Now the last part here is just a few sound questions or waves questions, which just a wee bit of revision. So the diagram on the right represents one type of wave. What type of wave is it? And of course it's a longitudinal wave. Describe carefully how part A of the wave is moving. So part A is moving backwards and forwards like that. So it's moving, and this is really just a description of the movement of particles in a longitudinal wave. It's moving parallel to the direction of travel of the wave. And maybe I suppose we should put in the word here. I should have put it in before parallel. I'll put it here. Vibrating. So it's really only vibrating about its position. It doesn't move from there to the end of the wave. Use the diagram to determine the wavelength of the wave. Now, if you remember that the wavelength of a longitudinal wave is from one point in one wave to exactly the same point in the next. So it's from the middle of a compression to the middle of the next one. So if we just count how many of those we have, there's 1, 2, 3. So there's 3 wavelengths. So 3 lambda is equal to 12 meters. And therefore lambda is equal to 12 divided by 3, which is 4 meters. The frequency is 2.5 Hertz. Calculated speed, show all working out. So we now have a wavelength. We know our wave equation. V is equal to lambda f. Lambda is 4. F is 2.5. And the answer is 10. And because our wavelength is in meters, the answer is meters per second there. So the answer is 10 meters per second. The next question. The water waves in the diagram below travel from deep to shallow water. Complete the path of the wavefronts into the shallow water by first continuing an arrow, and that arrow represents their direction in the deep and shallow regions. So if I just get a ruler here, you can see that there's already a ray on this, so to show the direction of travel. So we'll just finish that off there, and there's where it hits the boundary. There's a normal, and because it's going from deep into shallow water, then it bends towards the normal like this. Okay, now whenever it goes on into the normal, you can, into the shallow water, you can continue these wavefronts. So I'm just going to draw a couple more in the deep water first, and they should have the same wavelength roughly here, and then that'll help us join up whenever it gets into the shallow water. So one more maybe about there or so. Alright, so these then, whenever we put them into the shallow water, they have to be at right angles to the ray that we drew there. So that's at about there. And if we draw a few more parallel, join them up like that, we can see then that the new wavelength is much smaller. So we're just going to continue them on then into the, and we'll just kind of guess what they are. They have to be more or less the same distance apart. Well, they're supposed to be exactly the same distance apart. One more and do. Right? So what you have there then is you have your new ray. We've drawn a few more wavefronts here and then just joined them up at the boundary, but we've made sure that these new wavefronts in the water are at right angles to the ray that we drew, and then they're closer apart. So lambda is that, whereas lambda up here is much bigger. And that's continuing your diagram. A sound is played into a microphone which is connected to a CRO. The display is shown below. How can you tell from the shape of the display that the sound has a constant frequency? So you can tell because the wavelength is unchanged. You can see the distance between one peak and the next is exactly the same. Describe fully how the shape of the display changes when the frequency of the sound changes from 400 to 200. So if the frequency goes down, then the wavelength goes up. And so therefore, lambda becomes greater. And you can be even more specific than that. Because the frequency has been reduced by a half, the lambda has doubled. The wavelength has doubled. Last question, and this is an echo question. Fishing boats use ultrasound to find shoals of fish. Underline the correct words in the sentence below which describe an ultrasound wave. So ultrasound is of course it is a sound wave. It has a frequency, and that frequency is greater than 20 kilohertz, which is this one here. And then there's a calculation question. A fishing boat sends out an ultrasound pulse which travels through the water at 1500 meters per second to the shoal of fish. The time between the transmitted pulse and the received pulse is 0.2 seconds. So that's your echo time. And this is your speed. So this is what I was telling you to watch out for. We're looking for the total distance travelled by the ultrasound pulse. So we can get away with just using speed equals distance over time. And distance is speed by time. And that's 1500. Now we're using the echo time because that's the distance travelled down and up, and we are being asked for the total distance. So it's 1500 times 0.2. And that gives you an answer of 300 meters. But it's much more usual they ask you to calculate the distance to the shoal of fish. And when you do that, either you've divided your time by 2 before you do your calculation, or you divide your answer by 2. So because we've already got our answer, we're just going to divide it by 2. So that's the distance up and down again, and therefore that's 150 meters. Shortly after the first echo is received, a second is received. Explain. And the most likely explanation is there. They've got the first echo from the fish, and the second echo is then the sound returning from the seabed beneath. And that's the end of Unit 8 podcast, Waves and Sound. Thank you.